Hi, and welcome back. So, the first topic we're going to talk about in this course is glycolysis. So, you've already watched the big picture, so first let's talk about where glycolysis fits in. But before we do that, let's talk about a couple of things we're going to do just systematically on how we're approaching this video. I want you to have the PowerPoint available to you. So at least at the beginning, I'll start out with the PowerPoint, but it's a doing and a drawing class. So we need to be able to draw. The easiest way mechanistically, I think, to do that is to keep switching back and forth between two screens or two PowerPoint presentations. So we'll do that. And we'll do our drawing within the PowerPoint. Because we're switching back and forth, it's easier to leave it not in slideshow in terms of the software and getting hung up with that. So let's talk first about where things fit in. So what you did in the past couple of days was you watched the big picture. So in the big picture, you looked at overall, what are we doing with metabolism? So what we're really talking about here is cellular metabolism. Cellular metabolism is the broad term for how you take your fats, your carbs, and your proteins and make available to your cells a consistent supply of energy. So we said in the big picture, and we'll say it again now, we're going to start out with one carbohydrate, and the carbohydrate we tend to start out with is glucose. We're going to take that all the way to ATP. And we used the analogy of we're going to build a highway. So let's say we're going to build I-95. We're going to go from Holton, Maine to Miami with this highway. Well, real highway builders build the highway and build the on-ramps and the off-ramps all at the same time. We're not going to be real highway builders. We're going to be extra super duper efficient ones. We're going to build the highway itself first, then go back and add the on-ramps and the off-ramps. If we do it that way, the hard part's building the highway. The on-ramps and off-ramps are easier. So we're going to build the highway first. This is our highway going from glucose to ATP. So we're going to do it in pieces, though. It's like, let's say you were driving that route from Maine to Miami or whatever. You're probably not going to drive it all in one go, although you might. But let's say you're going to do part today, part tomorrow, part the next day. And then you're going to explain to me what you did. And you'll say, I went from Maine to New York to Delaware, Delaware to Georgia. I don't know. So what we're going to do is, this is our highway. We're going to do it in pieces. So the first piece we're going to do is we're going to take glucose to pyruvate, not to ATP yet. So this first step is a process called glycolysis. So this will be under our carbs heading. Glycolysis is a process that processes carbohydrates. So that'll be our first step. Then we're going to be able to say, well, we took pyruvate and we did the next part of the next part and so on. So a big point of the big picture was to give us a map so you can say, I'm here, I'm here, I'm here kind of thing. So we'll use it for that. So first thing we're going to do, first place we're going to be is in glycolysis, going from glucose to pyruvate. So we're going to use this first process as a way of you, I guess, figuring out how you're going to approach these processes. So in our online this time, we're going to do the same thing over and over with each of our modules and sections of our modules. We're going to do the video. The video will use the PowerPoint, and the PowerPoint will be available to you. Then after the video will be a whole bunch of questions. I don't know how many a whole bunch is. I'll just keep adding to it as I see the need. Then you'll do the quiz. The point right now, or what your task is right now with glycolysis, is figure out how you want to approach learning processes. And I'll give you ideas and suggestions, things that have worked for other students as we go through. So my point in telling you that now is to tell you you're going to have a lot of processes to learn. And however you learn one is probably the way you're going to learn all of them. So in that sense, it's going to be very different than Biochem 1. But if you can get your system down now at the beginning, then that's going to make it easier as you continue through. And I'll help you get your system down. So we're going to do a whole bunch of processes, and all these processes together make up cellular respiration. Like we said, how you take your carbs, your fats, your proteins, and turn them into a consistent, available supply of energy for your cells. So we're going to take your convert your biochemical energy from the energy contained in those nutrients, probably best explained as the calories in your food, to ATP. We'll have some catabolic reactions, we'll have some anabolic. We'll have all those different 6 reactions that you learned last term. We're going to also talk about aerobic and anaerobic respiration. So aerobic respiration requires oxygen, anaerobic does not. So that's the strict, correct definition. Then we're going to talk about how it gets misused sometimes. So we've also talked about making ATP, taking the energy, the calories in your food, and using that energy and making ATP. We're also going to make some molecules that we'll use to make ATP. So we're going to use, and this is where our oxidation reduction reactions come in, we're going to take NAD, nicotinamide adenine dinucleotide, right here, and we're going to reduce our NAD to NADH. We're also going to take flavin adenine dinucleotide and reduce it to FADH2. So we're going to do that in several different processes. So let's talk about those now and get that out of the way. So what NAD and FAD are electron carriers. So there's going to be a lot of stories about electron carriers and putting the electron on the carrier, as in gaining the electron, as in reduction. So we're going to reduce NAD to NADH. We're going to reduce FAD to FADH2. So at the point at which the electron carrier is carrying the electron, as in when it's reduced, that's an energy-containing molecule. So what that really is like you writing a check to yourself for ATP. So NADH or FADH2 are electron carriers carrying electrons. They'll carry the electrons to the electron transport system, and that's where you'll use the energy contained in that electron to make ATP. So here's a simpler analogy for it. So NADH or FADH2, I should say, and FADH2 are like you writing checks to you for ATP. So think about a check. If I have a check, let's say my patient just paid their copay by writing a check, the little old lady who still writes the checks. I have that check. I know exactly what that check will be worth, but it's not spendable money right now. I can't go to Publix and buy chicken tenders with that check that somebody wrote to me. I have one more step to do to make it spendable money. That's my NADH and my FADH2. I know exactly what those are worth, how many ATP I'll get out of them, but they're not spendable, usable ATP. I've got to go to the electron transport chain, which we'll do in 2 weeks. That's where I'll cash my checks or take the energy contained here and get the ATP out of it. So then I have spendable, usable ATP. So we're going to make these molecules, NADH and FADH2, in a couple of different processes, including glycolysis. We call them ATP equivalents. So it's a little bit weird the way we say it. And what we'll say is things like NADH is 3 ATP equivalents. And there's a couple things I need to clarify with that number. So it'd be like saying a check for $30 is $30 equivalents. Sounds like 30 things, but it isn't. It's one check. So kind of like saying NADH is 3 ATP equivalents is making it sound like it's 3 things. It's not. It's just a weird way of saying I have this molecule that's worth 3 ATP. Okay, and let's talk quick about that number, and I'll bring this up again when we get there. Some of you guys who have recently taken biochemistry are saying, whoa, hang on here. What do you mean it's worth 3 ATP? It's worth 3 ATP, not accounting for heat. We're going to stick with some old terminology for a little while. And the reason is that the national boards have a ton of questions. They won't even tell us how many. So they have a ton of questions. So when something changes, it takes a long, long time to update. So until we know they're using or doing whatever resulted from that change, I'm not doing it. So some of you guys are saying, well, I just took biochem and we said NADH was worth 2.5 ATP. You're absolutely correct. You're accounting for heat. Kind of doesn't matter if you account for heat or not, as long as you're clear on what you're doing. The boards, the change that I last saw them make was sticking with the old numbers and just say not accounting for heat. We found an update in one of the textbooks where we account for heat now. We're not going to do that yet until we're sure they are. And I guess I'm looking at it too. It's more important for you to pass the boards and get your license than worry about half of an ATP. Half an ATP is not going to change the course of your career as a chiropractor. So we'll come back and talk about my numbers, but I just want you to have the logic for my numbers. Okay, something you're going to do here, put a little note around here and say, you're coming back to this. You are. I'm going to give you the tools, the information to come back to it, and then you're coming back to it. And here's what I'm talking about there. With this ATP equivalent idea, you can, let's go to the other diagram and talk about it. So in the big picture, you did glycolysis, then you talked about the pyruvate dehydrogenase complex. Then you did the Krebs cycle. Then you did electron transport. Oops. And these processes, or most of them, make ATP equivalents and all that. But in the end, what we want to do is we're going to be looking at this glucose and saying by the time we get all the way down here to ATP, how many ATPs are we getting out of it? So I'll make a deal with you. And we kind of made this deal last term a little bit. We're not going to balance equations and count carbons and hydrogens and oxygens and get too crazy there. We'll get a little bit. We made our deal with structure. We're not going to do the name it, draw it, name it, but we are going to pay attention to the pertinent parts. So we're not going to get super crazy on, I'm short one carbon on this reaction, whatever. But what we are going to do is count and account for ATP. I'm going to use a lot of money analogies because to manage your everyday life, you think in money. So you have experience doing that. You don't have experience necessarily counting and accounting for ATP. So I find it works better sometimes to bring it back to using money. So anyway, in these processes, I'm going to make some equivalents and I'm going to make some ATP, some equivalents, and so on. So you're going to decide, do I want to assign the ATP to the process in which I make the equivalent or to the process in which I turn it into real ATP? So let's put that in money because it's probably more straightforward in money. You're in your office and you're sitting down with your accountant, setting up your books and everything. And are you going to, let's say I'm your new patient, I come in today and I pay with my insurance. And today's, 8th of the month. You're going to submit my insurance and say get paid, 20th. I'm making it up. So are you going to assign, let's say, the $150 from my visit to today, the day you saw me, the day you got the equivalents, or are you going to assign it to the 20th, the day you actually get that money in your hand? You're probably going to do whatever your accountant tells you to do, but I hope you're seeing my point there. I can count the money on the date of service, or I can count the money on the day it actually goes in my bank account. So that's what we're talking about here. Are we going to count the ATPs in the process in which they're actually made, or are we going to count the ATPs in the process in which we make the equivalent? Doesn't matter as long as you know what you did. So that's what you're going to do. You're going to make that decision after we've done everything and come back and decide if you like those numbers or not, or if there's a different way you want to do it. Okay, so we're going to do glycolysis. We're going to do glycolysis. All right, why am I saying it like that? We're going to break down words. You're not actually officially taking medical terminology. It's, I guess, built into all your courses now, which is fine, wherever you get it, as long as you get it. But pay attention to it and use it. There's a lot of words that when you first look at them, you'll think, I don't know what that means, and it looks kind of big. But then when you think about it a little bit, it's like, easy. I know what that means. And you can use that. As we go through and start doing these processes, it's like, how hard is it? I only got 3 or 4 of them. But when you're sitting in boards and you have 6 tests in one morning or one afternoon or whichever, stuff blends together. So being able to break down words and use that will help you out. So we're going to do glycolysis. Glyco is sugar. GLU, anything, get your brain on carbohydrates, sugars. And since we're only doing carbohydrates right now, easy. But later on, I might ask you a question, you ate a ham sandwich and you had cheese on it, you had mayonnaise on it, and here's the rest of the question. Well, you're going to be wondering, all right, well, I've got a ham sandwich, so my ham is protein, my mayonnaise is fat, my bread is carbs. What are you asking me here? And you're going to have to be able to figure that out. Doing things like saying, okay, glyco, sugar, carb, that's helping me out. I'm on the bread, I'm in the carb part. Lysis is splitting. We're going to have a lot of GLU processes that really tend to blend together. So lysis is splitting. I'm going to split that sugar in this process. So we're going to do glycolysis in the cytoplasm. 2 of the things, and this is something to start thinking about to systemize you, Two of the things, or one of the things you have to know about every process is where does it happen? And here's why I'm one or two, both on the cellular level and on the tissue level. So glycolysis happens in the cytoplasm, the cellular level, in all of your cells on the tissue level. So we're going to come to a chart in a minute. We'll add that on there. It's really and truly an anaerobic process, meaning to get from the beginning to the end of glycolysis, I don't need oxygen. When I get to the end, whether I have oxygen determines what I do next, but to get to the end, I don't need it. Okay, so some other processes, the PowerPoint slides are still in here. We covered them in the big picture, just really to help you put the pieces together. And here's the thing about this class, and it's probably true of a lot of classes. There is no one difficult concept in this class. Your challenges are twofold. One is how does stuff fit together? What's the point? What am I doing here? And keeping stuff from blending together. The other one is how do these pieces fit together? Because we'll do one story, then we'll do another story or another process and another one. And then it's really easy for you to end up sitting there with a pile of notes saying, oh, this is great, but how do they fit together? Okay, so a couple diagrams. We'll come back and talk about that. We talked about it with the big picture already. Okay, where the glucose is going, we'll talk about that too. Okay, so glycolysis is splitting the sugar. It's a 10-step pathway. Who cares how many? You kind of care, you kind of don't. So a couple things with that. You could call it 10 steps, 11 steps, depending on what book you pick. With all of the processes that we're going to talk about, what I've done is gone through the books that are board required, accepted, I don't know what word to use. When you go on the nbce.org website, there's a list of books that are fair game to take the board questions from. So from that list, I've gone through those and I looked and said, well, how many steps do they have for glycolysis? How many steps do they have? Because you can count some intermediates, you don't have to count them. How do we decide? That's how I decided. So I just kind of did majority rules with that. So majority rules is 10 steps. We're going to do 10 steps, but when you learn the steps, don't learn them by the numbers, because I did majority rules, but it wasn't unanimous. And if you learn, well, step 7 is, and the question came from a book that counted differently, that's not your step 7. So, other thing with that is I did number the steps in the PowerPoint, and I found we need that to stay organized. I took them out, taught a couple of terms, and we were all over the place. So, for teaching purposes, the step numbers are in there. For learning purposes, don't learn them that way. Okay, another thing we're going to talk about is the kind of questions you're going to get asked. One of your skills that would really, really help you to develop, like we talked about last term, is the ability to predict questions. If you can predict questions, that systemizes and organizes your studying so well. So a really common multiple choice question to get asked on any process is, all of the following are products except, or all of the following are reactants except. If you come down to 2 answers on one of those questions, look and see if one of your 2 answers is something like NAD, ADP, FAD, things like that. Because if it is, here's what you did. We're going to spend a whole bunch of time talking about ATP. How many did we make? How many did we use? Things like that. We're going to talk about NADH. How many did we get? How many ATPs do we get? FADH2. How many did we make? How many ATPs did we get from them? We'll get so focused on these, it's really easy to forget to make an ATP, I needed an ADP. To make an NADH, I needed an NAD. FADH2 needed an FAD. So we just forget about these. So if you get all the following products or reactants except, and you have two answers, one of them is one of these, you probably just forgot that you either made one of those or used one of those. So don't memorize this equation. I only put it in there to remind really me to remind you of this. Okay, so like we said, we're splitting the sugar. Did I go the wrong way? No, okay. So we're splitting the sugar. Glyco is the sugar, lysis is splitting it. We're going to get ATP. That's our goal here, and we'll talk about the relevance of that. It's the simplest form of metabolism in the cell. That's a weird, loaded statement. And where that's coming from is the fact that we do this in the cytoplasm. So we're going to get a little bit of ATP with glycolysis. And I'm saying a little bit relative to what we can potentially get from that molecule of glucose. We'll get the bulk of it. Well, we actually get the ATP in the electron transport chain, but we'll get the bulk of the equivalents, the molecules that make the ATP, in the Krebs cycle. But the Krebs cycle happens in the mitochondria. Okay, so why is that relevant? It's relevant because all of your tissues, all of your cells have cytoplasm. Not all of your cells have mitochondria. So because all of your cells have cytoplasm, all of your cells can do glycolysis. That's what we mean by this. Not all of your cells have mitochondria. Not everybody can do the Krebs cycle. So simplest form of metabolism in the cell is just saying all your cells can do it because it occurs in the cytoplasm. Okay, so this is the diagram. Let's back up for a minute and talk. What we're going to do is we do this, and I've always done it even when we were in class, and I did it on paper years ago, is I'm going to help you go through, summarize the whole PowerPoint in a page or two. And that is what you can really study the whole thing from, as long as, and this is a big disclaimer, as long as you understand what's going on. So, as long as you understand what's going on, we'll turn this into a page or two, and I'll help you do it. So, what we're going to do is when you look at your syllabus and everything, which I hope you've done already, you'll see a project there and points for the project. Your project is actually going to be all these diagrams that you're going to make. The reason I'm having you do that is by making these diagrams, you're making your board notes by you for you. And it's the by you for you is the important part of it. So I could give you mine if you wanted them. If you want them, say so, you can have them. But kind of wasting your time with them, because one of your challenges, half the battle with this is obviously knowing the material. The other half of the battle is knowing what the question is asking you. So some of the questions, the wording is going to feel a little bit weird. So you're going to have to be able to dig through and say, what are you really asking me here with this question? For that reason, I'm going to ask you a lot of questions so you can get through that. We're also going to talk about a lot of questions or a lot of things, and I'll say, well, it could get asked this way, this way, this way. What you're going to do is make your board notes with by you, for you part that's so important, being whatever you need in those notes for you to pick up on the this way, or this way. So I'll walk you through the first couple so you'll kind of get it down and figure out what you like and what you want to do. So there's some different options with the diagrams too. When you get asked about a reaction on the boards, you're asked in words. So first reaction on here is glucose is converted to glucose 6-phosphate. If you get asked, what does glucose make? Your option will be in words, glucose 6-phosphate, not the structure. So because of that, some people will say, I want the diagram with the words. I'm going to get asked my questions in words. I want words to learn from. So we're going to do the first one in words, so you can try it and say, I like this, I don't like this. I've had students say, I like the one in words because it's cleaner, too, less clutter stuff on it. The next diagram we're going to do, a lot of them we're going to draw too, but the next one that we're going to do that I'm going to give you the structures. I like the structures because I like pictures, but it's just the way I think. So I'm going to go through and do this stuff on these diagrams. You can use my diagram if you like it. If you don't like it, go find another one. Google Images has a million of them. If you've taken biochem before and you have one from your old biochem class that you like, by all means use it. So whatever works for you, this is all about you, your board notes by you, for you. So we're going to do the notes, do the diagrams, and I'll walk you through them, get you going on it. Then at the end, you're going to put that all together and submit it. That will be your project. So it's kind of like the vitamin chart in the sense that it's no real difficulty, just do it. But the whole point of doing it is I want you getting your board notes together now as we go through while it's on your mind. And that's for two reasons. One is, even though you won't feel like it, you have more time now than you will the term, whatever term you take the boards. The other thing is, I get this all the time. Students will say, well, I'll put my notes together the break before the boards. You can, but you'll be far enough removed from it by then you'll have forgotten stuff, so you won't do it as well. And you'll be far enough removed from it by then that you'll have forgotten stuff. It'll take you twice as long to do it. So the points on the project are just kind of blackmail or bribery to do it as we go along. So anyway, I've pulled this diagram out, threw it in a separate PowerPoint, so that as we go through, I'll show you what notes I would make on it, and then you can follow along with me or do something different if you want. Okay, there's some other versions of the diagram. Again, whatever you choose. So the overall delta G of this process is a negative number. When I say that, you should be saying, well, yeah, no kidding, because a negative delta G, as you remember, means the process is going to go. If the process wasn't going to go, we're not going to spend our time on it. So we've got an overall negative delta G. But don't forget, that's my overall. That doesn't mean every reaction has a negative delta G. We're going to have some reversible reactions, delta G equals 0. We're going to have some reactions that require energy, but we have enough that produce enough more energy, there's some grammar, to drag along the reactions that need energy. Okay, so glycolysis is often broken up a number of ways, but one is into a preparatory phase and a payoff phase, or an investment phase and a payoff phase. A lot of different terms that sound like a spending money phase, then a making money phase. And it kind of is like that. So it's kind of like the old expression, you need to spend money to make money. You need to spend ATP to make ATP. So also, kind of like in your office, you're going to spend a bunch of money, you're setting it up, whatever, before you make anything. Same idea. So we're going to spend ATP first, then we'll make ATP. Okay, so the first reaction we're going to do, and same deal, I'm not really skipping anything in the PowerPoint. I'm just not going to read PowerPoint slides to you. You can do that. First reaction is a reaction where we're going to take a molecule of glucose. So here's my glucose, and we're going to phosphorylate it. We're going to get the phosphate that we're going to use to phosphorylate from ATP. So I have my glucose. Remember, my glucose is a ring structure. I've got my carbon 1, 2, 3, 4, 5, and 6. Happen to have a diagram without all the little C's drawn. But if you want your little C's drawn, put your little C's in there. Again, this is your notes by you for you. So I'm going to take that ATP and I'm going to break a phosphate off. So when I take ATP and take the phosphate off, or when I break it, I get two things. I get the phosphate and I get energy. I guess I get three things. I get the phosphate, energy, and ADP. So I take the phosphate off, break the high energy phosphate bond, get the energy to do this, and I get the phosphate. I'm going to take the phosphate and put it onto carbon 6. That gives me glucose 6-phosphate. Let's talk about a couple of things with abbreviations. If the word starts with G, don't abbreviate it. Write the whole thing out. And I know it's totally a do as I say, not as I do. It is, but do it. And here, the reason is you're going to have so many GLY, GLU words that I can predict down to 2 processes, down to the week of when they're going to start blending together on you. I'm not confident they will, because they will. So anything that starts with a G, write it out. So I get glucose 6-phosphate. P for phosphate, you're safe. It's the only P we have. We get to fructose, F for fructose, you're safe. It's the only F. But G's, write it out. So glucose 6-phosphate, meaning I put the phosphate onto carbon 6. So that's what I got. That's my first reaction. The enzyme that catalyzed it is hexokinase. Kinases put phosphates on molecules. So it's hexokinase. Remember in Biochem 1 when we were talking about cofactors and coenzymes. Very often an enzyme needs a helper. The helper is a little mineral or vitamin. In this case, it's a little mineral. I need magnesium. So I use hexokinase and I use magnesium. I get glucose 6-phosphate. What's really interesting with that is once that glucose has become glucose 6-phosphate, it essentially traps it in the cell. So your blood glucose levels could drop if that glucose is already phosphorylated, as in the phosphate attached. It's staying in the cell regardless. So we can end up with a concentration gradient that way, but we can, it stays in there. So what I would be doing then, if I were you, is I'd have my diagram then, and I would be writing on them. I started out with my glucose. I wouldn't underline stuff on yours, but I'll do it just to show you where we are. I converted to glucose 6-phosphate. My enzyme was hexokinase. I needed a magnesium. And this is a regulatory reaction. And we'll come back and talk about what regulates it. I would probably also, I use that ATP. I know I'm going to be counting and accounting for ATP. I'd probably put, -1 ATP or used one. Couple other things I would have on here though too would be cut of the things or some of the things that you need to know for every process. One is, what's the point of the process? The point is, I'm going to process, let's say start processing. Start processing my carbs for energy. All of your what's the point of your processes are going to have kind of a theme. The theme is going to be the what, the fat, the carb, the protein, and for what. Am I making energy out of it? Am I putting something in storage? Am I taking something out of storage? That kind of thing. So we're processing carbs for energy. Some of the other stuff I would have on it is some of my wares. Tissue level cytoplasm. Or I'm sorry, cellular level cytoplasm. Tissue level, all of them. I might even put, it's an anaerobic process. So that's some good stuff to know about glycolysis too. So if I'm going to have a one or two page summary, what we're doing on paper is one sheet back and front, so I guess 2 pages. This is some of the stuff I would have on it. Okay, so let's keep going. Okay, so next reaction. We're going to convert fructose or glucose 6-phosphate to fructose 6-phosphate. So my glucose 6-phosphate, and I'm going to convert it to fructose 6-phosphate. Safe to abbreviate F's and P's. What I'm going to do is I'm going to make an isomer. I'm going to rearrange the molecule. So we know the process is glycolysis. Glycolysis. I want to split it. The more symmetric the molecule is, the more energy is in my favor when it comes to splitting a molecule. And sometimes I say symmetric-ish. It's symmetric, but it's not symmetric in the sense that you can split it. And I'll tell you what I'm doing a terrible job of saying in a minute. So what we're going to do, though, is we have glucose 6-phosphates, we have the phosphate on carbon 6, and so on, in a 6-membered ring. 1 carbon's outside the ring. We're going to kick another carbon out of the ring. We're going to take carbon 1, and we're going to kick it out of the ring. So we're going to convert our 6-membered ring to a 5-carbon ring. So this carbon that was in the ring is going to end up out of the ring. We're making an isomer in a reversible reaction. We're making an isomer out of an already phosphorylated glucose. So remember our enzyme names. They were what they do, or what they do it to, with an A's on the end. So I'm going to make an isomerase, out of an already phosphorylated phosphoglucose. So it's a phosphoglucoisomerase. I'm not actually going to require that you know that enzyme. Here are the enzymes you need to know. You have to know the regulatory enzymes plus any others that have a particular significance. And well, it's been working for years. I was going to say I'm confident that this will work, not just because it's been working for years, but because you could figure out the rest if you needed to. I think the odds of you needing to are very, very small, but if you had to, you'd figure them out. So this one, I'm making an isomer out of a phosphorylated glucose, phosphoglucoisomerase. So when you go to your chart, not really anything to write. You might want to, I'm going to take the lines out from underlining stuff. Maybe. If you want to, you can make sure you really know your arrows. That first reaction, one-way arrow. Now, two-way arrows. So you might want to do that if you want. Regulatory steps have to be irreversible. That is kind of logical, but really, really important. Think about if you're going to go in direct traffic. If it's just you, and let's say it's an alley, two-way alley, can you control who comes in and comes out? Not really. You're at one end, you can direct traffic there, but people could be coming in and out the other end. If it's a one-way alley, absolutely, you can control that. You can regulate that. You're standing at the end of that alley saying, you can come in and you can't. So I can only regulate a one-way street. I can only regulate an irreversible reaction. Okay, next up is going to be really kind of the same as the first step. So I have my glucose 6-phosphate. Or I'm sorry, I have my fructose 1,6. What do I have? I have my fructose 6-phosphate. I'm getting distracted by my computer getting hung up here. Okay, got my fructose 6-phosphate. So I've got my fructose, got my phosphate on carbon 6. Remember with the first reaction what we did. Took the ATP, we broke the phosphate off, gave us an ADP, gave us the phosphate, gave us energy. We need the energy for this. We're going to take, and let's back up for a second on that. When you see an ATP getting used, and this is really important, when you see an ATP getting used, and by getting used, I mean getting converted to ADP and the phosphate. When you see that happening, we're always going to use the energy. We might use the phosphate or we might not. So the energy's an always, the phosphate's a maybe. But this time we're going to use both. So we already have the phosphate on carbon 6. Now we're going to put one on carbon 1. So this is my 6, this is my 1. That's going to give me fructose, 1 for 1 on carbon 1, 6 for 1 on carbon 6, bis phosphate. You already see you have 2, so I don't know why we say the bis in there, but we do. So these are the carbons it's on. Bis 4 saying this 2, phosphate, fructose 1,6 bis phosphate. The enzyme that does this is phosphofructokinase 1. So kinases put phosphates on, good thing to know. Put it on what? An already phosphorylated fructose. This is my committing step. This is my jump off the cliff step. It's kind of like when you jump off the cliff. If you decide halfway down, this was a bad decision, too bad you're going anyway. We're committing to glycolysis here. Even if we don't want to do it, we're doing it. So, couple things. Let's go to our diagram. And I would add some stuff. So I've got my fructose 6-phosphate, got a one-way arrow now, and a couple things. I used an ATP, and my enzyme is regulatory phosphofructokinase, abbreviated PFK, so phosphofructokinase 1. Needed a magnesium as a helper, and this is regulatory or committing. And what I have now is a fructose 1,6 bisphosphate. Okay, let's keep on keeping on. Okay, so I'm finally going to do the split part of glycolysis. We're going to do the lysis part. So energetically, the more symmetric the molecule is, the better shape we're in typically for splitting it. So we have the molecule pretty symmetric, but when we split it, we can't, split into two identical halves. This oxygen's got to go one way or the other. So we are going to split it, cleave it, and we're going to get two things. We're going to get dihydroxyacetone phosphate, DHAP, safe abbreviation. And with abbreviations, you guys, though, make sure you know the abbreviation either way. And the one that catches you a lot is ATP. When I ask you questions, I'm going to ask you or give it to you the way you're used to seeing it. But with the boards, as you know, there's people from all over the country asking or writing you questions. They might not say things the same way I do. So if I ask you about ATP, I'm going to give you ATP. Somebody else might give you adenosine triphosphate. So make sure with abbreviations you pick up on it either way. So like with DHAP, you have to know what it means also. So we get a DHAP and we get a glyceraldehyde 3-phosphate. Again, no G's, write it out. Sometimes it's abbreviated G3P, might be GAPD. Again, depending on what book you're reading, don't do it. Starts with a G, write it out. So I cleaved it. I got these two molecules. But I didn't really want that DHAP. I'm going to want it more later. When we start doing fats and everything, we'll want it. Right now we don't. So what we're going to do, I've got the split part done. I don't want this. I'm going to rearrange it into another, I'm going to abbreviate for here, into another glyceraldehyde 3-phosphate. When I say rearrange, I'm making an isomer. So I'm going to take my DHAP, rearrange it into another glyceraldehyde 3-phosphate. Again, you don't have to know the enzyme, but you'd figure it out. What am I doing? I'm rearranging. I'm making an isomer, isomerase, out of what? 3-carbon sugar, triose. Remember, ose on the end is sugar. Triose with a phosphate. Okay, let's go to our diagram. Okay, so the split part is actually reversible. And sometimes intuitively that doesn't sit right. When I say splitting a molecule is reversible, sometimes it's like, well, hang on, I broke something. What do you mean I can put it back together? You can. And when I turn around and say, well, if I have two little molecules and make a big one out of them, can I do that? Well, yeah, of course. So the terminology can catch up a little bit there. And again, this is the reason your notes are by you, for you, your words. So I take that fructose 1,6-bisphosphate and I split it into a glyceraldehyde 3-phosphate and into a dihydroxyacetone phosphate. What I really want is I want two glyceraldehyde 3-phosphates. And when I say want, I want it for this particular purpose. So then I rearrange that glyceraldehyde 3-phosphate into, my dihydroxyacetone phosphate into my other glyceraldehyde 3-phosphate. So at this point, I've got my two glyceraldehyde 3-phosphates. So at this point, I'm actually done spending ATP. So at this point, I'm actually done with the preparatory phase, investment phase, whichever term you want to use for that. So I have my two glyceraldehyde 3-phosphates. Let's look at something quick though. And this comes back to the diagram thing. If you look at this column and this column, they're identical. So This gets important when you choose whatever diagram you want to use. Some books will only have one column, and they'll have all these little tiny twos, two, whatever next to everything. They're 100% correct, and they're really, really dangerous. What I mean by that is they're dangerous because it's really easy to forget those little twos are there and not notice they're there. Because what you're going to do is you're going to do this class, you're going to do the course, you're going to take the final in June, whatever, and move on to other courses, other classes, other topics, other stuff, and have about a year-ish to forget all of this. And I'll hear you guys say, oh no, I'm going to study biochem for an hour a week and all that. No, you're not. You don't have time. I appreciate your good intentions, but realistically, you don't have time. So you're going to forget stuff. And these little twos are one of the things that get really easy to forget. Also, most of you guys are visual learners because most people are visual learners. I would have these two columns right here in my face on that diagram, so I can't possibly forget I have two of everything. The other thing you're going to notice is it probably happens in every topic, but in this one, it just seems more obvious, more blatant, and maybe it's because this is the one I teach. But when you look at a multiple choice question and look at the distractors, the wrong answers, and look at the question, the correct answer and everything, it almost looks like whoever wrote the question, in a lot of cases, might have put more time into the distractors than the question and the correct answer. And what I mean is, one of the things that I've seen commonly is they'll have a question that, the answer's somewhere in here, and they'll say, okay, well, what if they forget there's two of that molecule? What answer would they get? Let me give it to them and see if I catch them, stuff like that. So whether you want words, pictures, multicolor, whatever, have at it. Do what makes you happy. If you want to draw it, do it. But have these two columns. You're just living way too dangerously if you don't. The other thing is, as we continue the conversation, I should be saying these two molecules make these two molecules and things like that. I won't. I'll forget. Everybody does. So that kind of thing makes it even easier to think I have one of this molecule and one of that or whatever and mess you up even more. So choose your diagram. Like I said, I don't care if it's mine or not. It's whatever makes you happy. I chose these two just to give you two examples. And, do whatever you want that way, but I would absolutely have these two columns. Okay, let's go back. I think we're going to find a good stopping point simply because if the video gets too long, it's a pain to render. Okay, we're awful close to that. So what we've done so far is we took that one glucose, we have 2-glyceraldehyde 3-phosphates out of it. Now, we used 2 ATPs. Getting to that point, we got no ATPs. We have 2 enzymes we need to know. We need to know hexokinase because it's regulatory. We'll talk about what regulates it. Phosphofructokinase because it's regulatory, and we'll come back and talk about what regulates it. Okay, we're going to go into the payoff phase next. I'm going to stop the video and do a part 2 just so it's not too much of a beast to render. So we'll be back in a minute and do that. Okay, so let's keep going. So what are we doing? We're doing glycolysis, splitting the sugar. We're starting to process our carbohydrates with the end goal of making energy in mind. We want ATP. So what have we done so far? We started out with a molecule of glucose. We took the glucose, we used an ATP, used a molecule of hexokinase, a magnesium, and made glucose 6-phosphate. Irreversible reaction, regulatory reaction, and we're going to come back and talk about what regulates it. So we have our glucose 6-phosphate. We know that we're going to split the molecule. That's the lysis part of this. We know that energetically, the more symmetric-ish the molecule is, the better shape we're in for splitting it. So we rearrange that glucose 6-phosphate into a fructose 6-phosphate. Used an isomerase to do that in a reversible reaction. Then we did our third reaction, in which we did basically the same thing we did in the first one. We used an ATP, used another kinase, phosphofructokinase this time, a magnesium, split the ATP, broke the high energy bond for the energy and a phosphate, and we made fructose 1,6-bisphosphate. Then we're finally ready to split. So we split the molecule into a glyceraldehyde 3-phosphate. We were happy about that. And a dihydroxyacetone phosphate. We're not so happy about that yet. We'll use it later when we're making fats, telling the fat story. But we don't really want it now, so we're going to rearrange it into another glyceraldehyde 3-phosphate. So at this point, we have 2 glyceraldehyde 3-phosphates, and we're ready to continue on and finally get some ATP out of this. So the next thing we're going to do is we're going to take, I should be saying those glyceraldehyde 3-phosphates, I won't remember, and we're going to oxidize them. So let's talk about oxidation and reduction. So we said there's some molecules and parts of molecules that if we make them, we're just going to leave them there, so we can leave them there. And that's all about the scope of the class. Another class will talk about what you're really going to do with them. You're not leaving them there. Things like water, carbon dioxide, things like that. Then also with molecules like that, like if we need water, we'll assume one's there. A physiology class will talk about why it's there, how it got there. But there's some things that we don't just leave there or have hanging out waiting for us. Electrons are one of them. So if I want an electron, I've got to get it from somewhere. Meaning, if I want to reduce something, if I want a molecule to gain an electron, another molecule has to get oxidized. Another molecule will lose an electron. I can't oxidize without reducing. I can't reduce without oxidizing. So that's half of the story. The other thing is when we oxidize something, the molecule we're reducing, the other half of that oxidation reduction thing, is typically an electron carrier, meaning we're loading an electron carrier up with an electron, meaning we're getting an ATP equivalent, meaning we're getting a molecule that will give us ATP. We're writing a check to ourselves for ATP. So what you're going to start doing is getting in the habit of when we say we oxidize something, say to yourself, what did I reduce? Total what's in it for me question. Not that there's anything wrong with those. But what did I reduce? What did I get? Is like, what electron equivalent or electron carrier ATP equivalent did I just get? So what we're going to do is we're going to take that glyceraldehyde 3-phosphate and we're going to do 2 things to it. We're going to oxidize something. So your what's in it for me question is what did I reduce? I reduced NAD to NADH. That's what I got. That's an ATP equivalent. We like that. Also, let me back up for a second. Typically, traditionally, the concept of ATP equivalence isn't brought up until the Krebs cycle. What I've found is whatever I'm saying, however I'm teaching it, if I bring it up when we're doing glycolysis, it tends to be a 5-minute discussion. If I wait until the Krebs cycle, it tends to be a 30-minute discussion. I don't know what I'm saying differently either way, but that's just the way it is. That's why I'm bringing it up now. So for you guys who have taken biochem before and you're thinking, why is she bringing it up now? That's why. Or if you're watching a video on YouTube and it's not brought up and you're wondering why, again, that's the why. So that's going to go and give us ATP later. For now, we got NADH. The other thing we're going to do is we're going to take a phosphate, this time from solution. One floating around is a way of looking at it, not attached to an ATP, and we're going to attach it. So we already had one phosphate on there. We're going to attach another one now. So we took that glyceraldehyde 3-phosphate. Now we have 1,3, phosphate on carbon 1, phosphate on carbon 3, bis, redundant, but telling us there's two of them, phospho, 2 phosphates, glycerate. So I would go over to my diagram then. And I'm going to get rid of some stuff just to make room, make it a little less cluttery. Yeah, we can get rid of a lot of my clutter. Well, maybe we should have kept the arrows. Those were reversible arrows. Let me clutter it up again. And we were here. So this is the start of our payoff phase and where we are. So what we're going to do now is we're oxidizing. I guess green's a good color. Oxidizing glyceraldehyde 3-phosphate while we reduce NAD to NADH. So I got one NADH, but of course I should be speaking in plural, but I forgot, like everybody does. Got one NADH, got one NADH. Also phosphorylated the glyceraldehyde, so I have 1,3-bisphosphoglycerate or glycerophosphate. Be comfortable with that going either way, phosphoglycerate, glycerophosphate. Some books will do it one way, some books will do it the other. So glycerate 1,3-bisphosphate. Okay, so, and not regulatory, it's reversible. So you can do your two-way arrows if you want, and I wouldn't worry about the enzyme. Okay, so I've got the 1,3-bisphosphoglycerate or the glycerate 1,3-bisphosphate. What I also have, I have that molecule, and that molecule has a couple things. The molecule has the phosphates on it. The molecule also contains a bunch of energy. So remember, when we want to make ATP, we need a couple things. We need ADP, you won't forget that. We need the phosphate, but we also need enough energy to make a high energy phosphate bond. That's kind of the unwritten, forgotten part. So don't forget that part, even though we don't write it. So this molecule just so happens to have the energy we need. Since we have the energy, we're going to take a phosphate off, put it onto ADP, and make ATP. So we'll go from 1,3-bisphosphoglycerate to just 3-phosphoglycerate. We want to take that phosphate that was on carbon 1 off. The enzyme that does this is phosphoglycerate kinase. Figures, phosphoglycerate and kinases put phosphates on. So you have to know that enzyme, but it's not regulatory. So that's the one that messes you up. So a couple things I can write here. Got an ATP. But of course I'm doing both. So I got 2 ATP. Got 1 ATP over here. This enzyme or this reaction is reversible, not regulatory. Remember, got to be irreversible to be regulatory. But you have to know the enzyme. The enzyme was phosphoglycerate kinase. Okay, why do I have to know it? I have to know it because it's the enzyme that catalyzes the first reaction of glycolysis in which you form ATP. So it'll be in your questions. You're going to see this 100 times because it's just an old traditional, turned up all the time kind of a question. Which of the following enzymes catalyzes the first reaction of glycolysis in which you form ATP? So pretty easy. Stats on that question tend to be pretty good. Here's where it catches you though. Another common question, and again, I'm giving you these because I want you thinking about these as you're studying. This will direct you because otherwise you can end up looking at this like, what do I do? Where do I start? So another common question is, all of the following enzymes regulate this process except the most common except, we're going to have one more regulatory. The most common except is your phosphoglycerate kinase. And what whoever's asking you that question is doing is seeing if you remember that it's not regulatory. Because you remember, I got to know all my regulatory enzymes. You remember, I have to know phosphoglycerate kinase. Do you remember, though, you have to know phosphoglycerate kinase, even though it's not a regulatory enzyme. So it's not regulatory. You still have to know it because it's the enzyme that catalyzes the first reaction of glycolysis in which you form ATP. So really important that you know that. Okay, let's go to reactions. Okay, so I'm going to go through a couple of steps, and what I'm going to do is I want to get another phosphate off, and I want to have enough energy contained in that molecule so that when I get the phosphate off, I can make an ATP out of the phosphate I take off and an ADP. So sometimes when we make isomers, we're going to make an isomer that's less stable. This bothers the organic chemists, and that's why I say it over and over, because what I don't want you to do is to be sitting in a test saying, "Oh, hang on here, that can't be what I'm doing, because that's actually making a less stable molecule. You know, I like my molecules stable." They hammer that into your head in organic chemistry. So, except in what we're doing, sometimes we're getting less stable. The reason we're getting less stable sometimes is we have a particular thing we want to do, a particular reaction we want to do, and we might not have enough energy to do it unless we get less stable. It's kind of like, I don't know, let's say you have $5 in your pocket. Your goal is to have lunch. And you think, oh, Outback sounds pretty good. Well, $5 in the Outback isn't going to happen. Well, if I rearrange my plans, maybe go to Taco Bell. I don't know, can you still eat at Taco Bell for $5? Anyway, $10 maybe. If I rearrange my plans, now I can accomplish that goal. If I rearrange the molecule, make it less stable, maybe I can accomplish my goal. So what I'm going to do is I'm going to move the phosphate over next to the carboxyl group. If I take parts of the molecule and push them closer together, cause steric hindrance. I know you organic chemists hate that, causing steric hindrance. I'm going to make it less stable. More steric hindrance, less stable. So I'm going to do that. I'm going to take my 3-phosphoglycerate, make it a 2-phosphoglycerate. The phosphate's next to the carboxyl. So this is basically what we said. We didn't have enough energy, so we rearranged the molecule to make us have enough energy. Okay, so another thing I'm going to do is I'm going to dehydrate the molecule. I'm going to pull the water off. Again, what I'm doing is I'm making a less stable molecule by doing that. I'm making that molecule just want to kick that phosphate off. So not a lot to write on our diagram yet. So finally, I end up with a phosphoenol pyruvate. That enol form just wants to kick that phosphate off. So it's going to do that. It's going to kick the phosphate off, leave me with a pyruvate. I have my ADP hanging out waiting. I put the phosphate on and I get an ATP. So the enzyme that catalyzes this is again a kinase, but it's a pyruvate kinase, making me that pyruvate. So now there's something worth writing on our diagram. If I can get to our diagram. Okay, so reversible reaction, nothing crazy to write. Reversible reaction, nothing crazy to write. Got our phosphoenol pyruvate, just dying to kick that phosphate off. It does, makes us an ATP. Got an ATP, but of course we did it twice. Got an ATP. The enzyme that does this is pyruvate kinase, another kinase. And this one is regulatory. So, got all my ATPs, got my pyruvate, I'm done. So let's go back and talk about some other things with glycolysis. So let me go back to the PowerPoint, make sure I do it in the order. We'll try to do it in the order it's in the PowerPoint in. So, got my two NADHs, forgot those. Don't care an awful lot other than to know I got them. We'll talk about the ATP they give us later, but I got those for ATP. Let's just do some stuff and then we'll use the PowerPoint and make sure we did everything. All right, what am I going to do? I'm going to put a new slide in and just put the ATPs on it. All right, so we'll just use a couple new slides to do our stuff now. I'm going to do a terrible job following the PowerPoint, but that's fine. All right, so I'm going to do pluses and minuses. So minus 1 ATP here, minus 1 ATP here, plus 1 ATP, plus 1 ATP, plus 1, and plus 1. Okay, so there's some terms. Let's go back to money. I know you hate it, but we're going to do it that way because you have to think in money. You're going to run a business. You've got to run your life now. You're going to run a business shortly. So when we're talking about money, there's certain things you have to know to talk about it. Well, let's go back to ATP first. Then you'll know where I'm going. So probably about 10 of your 50 questions on the final this term are going to start with how many ATP, whatever. So the stuff you have to know before you could answer a how many ATP question. First one is per what? So it's like how much money? How much money do you make in your office? Well, per what? Last week, last month, last year, per what? Give me a reference point. Same thing with ATP. Per what? So we're going to start this conversation. How many ATP did I make per glucose? Then with money, there's a couple more things you have to know. You have to know how much money did you make in your office last month? Well, do you mean how much money did I bring in the door, or how much money did I have left after I paid all my bills? So what I'm talking about is profit versus gross. So the gross is the total amount of money you brought in. Profit's what's left after you paid your bills. The other thing is, if I say, how much money did you bring into your office last month? Do you mean spendable cash, like cash on hand? Or are you counting like the insurance that hasn't paid me yet, the credit cards that I haven't gotten the money from yet, and stuff like that? That's my real ones versus equivalents. We'll come back to that. So what we're going to look at is the per what and profit versus gross. So if I start out, we'll pick colors for different stories. We're going to say per glucose. And what we're going to talk about first is how many did I made versus net or yield. Those are the biochem words you're going to see. So net or yield. So per glucose, how many ATP did I make? This is my gross, not counting anything it cost me to make them. I made 1, 2, 3, 4. So per glucose, my made is 4. My net or yield is what's left when I pay my bills. So I made those 4. It cost me 2. So 4 minus 2, my net or my yield is 2. So what I always tell students to do is when you're asked how many ATP do you make, net, yield, whatever, put your finger on your per what and your fingers on the end and count in between. I make 1, 2, 3, 4, costs me 2, 4 minus 2 is 2. Okay, let's do something else. Let's say you are, I don't know, you get up this morning and you're getting your cornflakes all ready and you're going to throw a banana in your cornflakes, so you ate a banana. And from that banana, you got a molecule of fructose 6-phosphate. And I want to know, per fructose 6-phosphate, how many ATP did you make? So you're going to put your finger on fructose 6-phosphate, fingers on pyruvate, and count in between. I made 1, 2, 3, 4 ATP. Or I might say, how many ATP did you net or yield per fructose 6-phosphate? Finger on fructose 6, fingers on pyruvate. I made 4, 1, 2, 3, 4. Minus how many did it cost me? Cost me 1. So my net or my yield is 3. Or let's say, here's one. And I know this is sounding like just an academic exercise right now and feeling that way. As we continue and do stuff, you'll see why we're doing this. Let's say you are, I don't know, you were hanging out last night and you decided to fire up the grill and you threw a nice marbled ribeye on the grill. What you'll learn later this term is that when you break down that nice ribeye, that marbling is actually triglycerides. When I break down triglycerides, I'm going to get a dihydroxyacetone phosphate. So my question for you is, how many ATP am I going to make per DHAP completing glycolysis? So it's per dihydroxyacetone phosphate. Put your finger on DHAP, your finger on the end. I've only got one DHAP, so I'm only on one side here. So how many ATP do I make between here and here? 1, 2. How many ATP do I net or yield? I made 2. I used none because I came in here. 2 minus 0 is 2. So be prepared. Be prepared for made versus net and yield kind of questions. Okay, so let's go back to the PowerPoint. I'm doing a terrible job following. That's okay. Okay. Let's do this aerobic anaerobic thing quick before I'm just going to totally forget it. Okay, so let's go back to the big picture for a second. We'll just draw it. All right, so we took glucose, we went to pyruvate. This is our glycolysis, and this is really and truly an anaerobic process. What we would like to do is we would like to continue and get ATP out of the molecule. That's our goal. That's what we're doing this for. Remember, in the big picture, we said to do this, we need oxygen. And the process we're going to go into, if pyruvate has oxygen, is the pyruvate dehydrogenase complex. Then we'll go to the Krebs cycle, electron transport, and so on. So if we have sufficient oxygen, we're going to do that. If we don't have sufficient oxygen, we're going to do this process called the Cori cycle, and we're going to do it in a couple minutes. This is the route that we're going to take if we have insufficient oxygen. So, easy enough, but here's some terminology that can kind of mess with you. You'll see the terms aerobic and anaerobic glycolysis. I'm not going to use them with you. Glycolysis really and truly is an anaerobic process. But this is a backhanded way of telling you which way pyruvate is going. I hate this. But anyway, it doesn't matter if I hate it. You need to be prepared for it. So, if you get a question on aerobic glycolysis, I mean, your first thought is, well, hang on, it's not aerobic, it's anaerobic. What are you doing here? What they're doing is, it's a backhanded way of saying that you have enough oxygen. Let me change that need to have it. You need it, but you're going that way if you have it. So this is the direction you're going to go if you have the oxygen. So if somebody says aerobic glycolysis, backhanded way of telling you have oxygen, very likely a pyruvate dehydrogenase complex question, possibly a Krebs cycle question. Other way around, if they say anaerobic glycolysis, your first thought is, well, yeah, I know that. That's kind of redundant. Again, it's referring to what pyruvate's seeing. Pyruvate's seeing insufficient oxygen, it's very likely a Cori cycle question. Cori cycle question without saying Cori cycle. So again, I'm not going to do this to you, but I want you prepared for it in case somebody else does. All right, so let's do regulation. That's the next thing in the PowerPoint. If you look at the PowerPoint and look at the slides on regulation, it's a lot of stuff, a lot of junk, a lot of words. It doesn't need to be that complicated. So let's do it not complicated. All right, so for regulation, let's just do it. I have 3 regulatory enzymes. I have hexokinase, I have phosphofructokinase, and I have pyruvate kinase. And I'm just going to abbreviate them. You have them spelled out on your diagram. So even though I'm abbreviating, make sure you know what they mean. All right, so there's a couple of things you need to know to make regulation much, much easier. So all you have to know, let's back up. All right, let's say we have no windows in the room, whatever room you're sitting in right now. What regulates whether the room is bright or dark? What regulates it is whether you turn the lights on or off, right? So what these regulatory enzymes do are they become activated or they become inhibited. So we turn glycolysis on or off. So we're going to go back to the point of the process in terms of deciding, do we want it turned on or turned off? So the point of glycolysis is I want to start processing my carbohydrates for energy. So when do I want glycolysis turned on? I want it turned on when I have carbs and when I need energy. When do I want it turned off? I want it turned off when I don't have carbs or don't need energy. So, pretty simple there. So, when do I want the lights on? When the room's dark and I want light. When do I want them off? I want them off when I want it dark. So, easy there. Lights on bright, lights off dark. Then I've got the on-off switch. All I have to know is who's going to turn the lights on and off for me. Who's going to tell me it's bright or dark? All you've got to know here is who's going to turn the enzyme on or off. And you can reason through the rest of it. So let's talk about the first regulator. What regulates hexokinase is your glucose 6-phosphate concentration. Okay, well, does that turn it on or off? Let's reason our way through it. If I already have a whole bunch of glucose 6-phosphate, are you confident I can go from glucose 6-phosphate to pyruvate through the pyruvate dehydrogenase complex, Krebs, and all the stuff I need to do to make ATP? Yeah. If you're in try 2, are you confident you can get to the end and get out of here? Yeah. Do you need to go and do try 1 again? No. If I already have glucose 6-phosphate, do I need to go and convert more glucose? No. So my effect is glucose 6-phosphate is an inhibitor. In fact, we call it product, since it's the product of the enzyme, product inhibition. So there's my hexokinase. Glucose 6-phosphate's the regulator. That's all I got to know. I can figure out it's going to inhibit, because if I already have glucose 6-phosphate, I'm confident I can get to pyruvate and as a result get to ATP. All right, let's look at phosphofructokinase. So, I don't know where my big picture is, so I'll just draw another one. What am I doing? Taking glucose, I just did glycolysis, went to pyruvate. I want to take pyruvate through the pyruvate dehydrogenase complex, do the Krebs cycle, which just so happens to have citrate as part of it, make the stuff to make ATP, and make it. So my goal is ATP. So I've got this enzyme up here, phosphofructokinase. One of the things that regulates it is citrate. So if I'm up here deciding whether to turn that enzyme on or off, my goal is to get to ATP. If I've already have this molecule that's so much closer, are you confident you can go from here to here and get the ATP you need and not have to do more stuff up here? If you're in, I don't know, try 7, do you want to be back doing try 2 stuff, or is that all done and good in ancient history? That's done good ancient history. You're good. You're going to get down here. So if I'm already here, I'm in try 7, I'm not even thinking about try 2. I can shut stuff down up here. And of course, if I'm shutting down phosphofructokinase, all the molecules above it can go and do other things, get stored, saved, do other stuff, whatever. So one of my regulators on on phosphofructokinase is citrate. And knowing that citrate's way down here, so much closer to my end goal, it's an inhibitor. Okay, let's talk about something else. We don't have to drill down some of the detail. We don't have to drill super deeply into. So, and sometimes it's better to stay a little bigger picture with it. So we're going to talk about two things, different ways I could say I have energy versus ways of saying I need energy. And some of this, one of the reasons I do this is I want you to have some terminology for some questions. If I have ATP, obviously I have energy. If I don't have ATP, I need it. So that's a way of saying I don't have energy. If I say I have ADP or AMP, take that as being told you need energy. And the reality is you always have all of it. Right now you have ATP in your cells, you have ADP in your cells, and you have AMP in your cells. You're always turning it over. Like in your office, you're always spending money, making money, spending it, making it. Always turning it over. But if a question specifically calls out you have ADP or AMP, more commonly it'll say you have ADP, they're trying to tell you you don't have energy, you need energy. Also, if the question says you have NADH or FADH2, take that as you have energy. You're okay in the energy department. And what I mean by that is, like, let's say you were really, really busy in your office today, but you didn't take in any cash. Everybody was insurance, wrote you checks, paid with their credit card, debit card, whatever. Do you care? No. You'll have the money, you just don't quite have it yet. So that's the ATP equivalence. I don't have the ATP yet, but I can get it. I'm good. If you told you have that you don't have NADH or don't have FADH2, of course, it's a need energy. Or if you have NAD or FAD, it might be a way of telling you you need energy. Or if it's called out in a question, it is a way of saying you need energy. So the other thing that regulates phosphofructokinase is energy. So all I've got to write is energy because I know any of those mean I have it, any of these mean I don't. But, well, hang on. Does energy activate or inhibit? Reason your way through that. I have this process that takes my carbs and starts me on the road to getting energy out of them. If I already have energy, do I need to do the energy making process? No. If I have energy, I can go and do something else with those molecules. If I don't have energy, do I need to do the energy making process? Yes. So energy is an inhibitor. Pretty easy, right? Okay, so our last one is pyruvate kinase. It's regulated by a couple of things. One is energy. Easy. It's an energy-making process. If I already have energy, I don't need to do it. If I don't have energy, I better do it. The other thing that regulates pyruvate kinase is fructose 1,6-bisphosphate. Oh, where'd I see that? Here we go. Here it is. So it's upstream. So here's the logic here. Let's say, I don't know, let's say next Friday you have tests in every class but mine. Now we'll throw one in mine too. So you have a test in every class next Friday, but you're acting a little bored. So let's say I don't want you bored. So I'll give you a biochem project, and it's going to be a big one. If you're going to do a project, you might as well do a nice big one. So it's going to be due next Thursday, but I'm not going to assign it until Tuesday. So here's the situation you're in, and I am kidding on the project, just trying to make a point. So here's the situation you would be in. You already have a bunch of work on your plate, and you know more work is coming. So what does it make sense to do? Get going and get the work you have done, or just hang out and take a nap and go to the beach? If you know you have more work coming and you have work now, the logic would be get rid of the work you have to make room for what's coming. That's what pyruvate kinase is going to do. It's going to say, well, right now I have this phosphoenolpyruvate here, but if I have a whole bunch of fructose 1,6-bisphosphate, I know I'm very shortly going to have a whole bunch more phosphoenolpyruvate. So I better take the phosphoenolpyruvate I have and convert it to pyruvate and make room. So fructose 1,6-bisphosphate is my only activator out of all these three. So inhibit, 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 activate. So does that make well, I know you can't answer me on video, but if it doesn't make sense, let me know and we'll talk about it. It's a whole lot less work to reason your way through it than try to say, well, this is want to activate, inhibit, and memorizing it. You don't want to be memorizing any more than necessary in this class for two reasons. One, there's enough stuff you got to memorize because you have to know what molecule makes what molecule makes what molecule and everything. So you don't want to add to that. The other thing is the kind of memorization you're most likely to mess up is either or. Well, does this activate or inhibit? Maybe it inhibits, maybe it activates. And the more you stare at the question, the more you second guess yourself. So reason your way through on that. Common way to get asked this kind of question is, here's the regulatory enzyme and the regulator in pairings. And when we get more processes under your belt, we can give you, like, say, a glycolysis pairing, hexokinase and glucose 6-phosphate, a Krebs cycle pairing, a pairing from another process, and say which pairing is incorrect. So all of the following regulate except is one common way. Pairings with the regulators is another common way. Okay, so that's regulation. And as you go through, there's an awful lot of words, an awful lot of stuff here. We'll come back and talk about glucokinase. That's how we store glucose. So we store it as glycogen. We'll talk about it then. But like what activates, what inhibits, and just stuff. If you slow down and reason through the way we did, it's a lot less work. And less work means less likely to mess it up. Fructose 2,6-bisphosphate, we're going to come back and talk about. We'll talk about it in the context of some hormones too. So anyway, more regulation. Okay, pyruvate can go a few different directions. Let's just draw the rest of this. Okay, so we said that glycolysis is taking glucose to pyruvate. If we have sufficient oxygen, we're going to go to ATP with it. That's our goal, that's our intention, that's what we want to do. If we don't have sufficient oxygen, we have this do-over loop idea called the Cori cycle. And what the Cori cycle does is it'll regenerate that glucose for you. And what it's trying to do, it'll get your glucose back so that you can again take it to pyruvate, hoping you have enough oxygen now to continue. If you don't, we'll get it back again. Try again. Do I have enough oxygen? Yes, I'll continue. No, I'll go back to glucose and try again. So let's do the Cori cycle. So most often, the Cori cycle story is going to be told in the context of an exercising skeletal muscle. So let's say I'm out running down Dunlawton Avenue. If you ever hear I'm running down Dunlawton Avenue, ask who's chasing me. But let's go with the story. So I'm running down Dunlawton Avenue. So what am I trying to do? My leg muscle, I have that glucose going to pyruvate. And this is my glycolysis. And what I would like that pyruvate to do is continue through all my steps, processes, and stuff and give me ATP to keep my leg muscles contracting, relaxing, and keep me running. But let's say I'm huffing and puffing and I'm not getting enough oxygen in. So that I get to pyruvate, the pyruvate looks around and says, I don't have enough oxygen here. So what it's going to do is go to a molecule called lactate. The enzyme that does that is called lactate dehydrogenase. So I don't really want lactate. So what I'm going to do with the lactate then is I'm going to send it to the liver. What you're going to notice about the liver is a couple things. Anything we don't want, we send to the liver. The liver cleans up after us. And any molecule that we're worried about having to all the tissues and stuff goes to the blood, and the liver takes care of the blood. So you're going to hear me saying a lot, the liver's like everybody's mama, takes care of everybody, cleans up after everybody. And that's what I mean. The liver's worried about the blood goes to everybody, all of your tissues. And you have a molecule you don't want, you want to get rid of it, the liver will do it for you. So I don't want lactate. I'm going to send it to the liver. What the liver is going to do is convert it to pyruvate. Lactate dehydrogenase will do that. Then, once I get it converted back to pyruvate, I've got this process called gluconeogenesis. We haven't done it yet. We'll do it, I think it's week 5. What that does is takes your pyruvate and makes glucose out of it. You kind of knew that though. Gluco for glucose, neo for new, genesis for generating. I could take that glucose, put it back in the bloodstream. It can go to that running leg muscle. In that running leg muscle, I'll take it, convert it back to pyruvate. Hope I'm huffing and puffing enough oxygen in to get to ATP. If not, I go to lactate. Send the lactate to the liver, back to pyruvate, back to glucose, back to the leg muscle. And I'll keep going doing this until I slow down and I'm able to get enough oxygen in. So, nuts and bolts. What do you tend to get asked about this? Well, the why. It's my kind of do-over loop to get the glucose back when I don't have enough oxygen. Or what do I tend to get asked? What enzyme? Lactate dehydrogenase, and we'll have a nasty distractor for it shortly. Where do I make what? I make pyruvate in the muscle, and then, or what makes what? Lactate dehydrogenase makes what where? Lactate dehydrogenase makes lactate in the muscle, makes pyruvate in the liver. I made pyruvate in the muscle by glycolysis. Then I take the lactate, convert it to pyruvate in the liver. So which way are you going is common questions. Okay, so that's everything. Let's talk about one more thing kind of quick. So we have different forms of lactate dehydrogenase, not super important that you know them, but let's talk about one more thing kind of quick. So the heart's a muscle, and it's a really, really special muscle in terms of function. In terms of the basic nuts and bolts biochemistry, though, In a lot of ways, it's just one more muscle. And what I mean by that is when you get down on the molecular enzyme, basic level, it's kind of just one more muscle, kind of like skeletal muscle in a lot of ways. And I'm bringing that up because sometimes when you're on the molecular level, if you forget that, you're thinking it as, some super duper special way of doing something that it really does the same way as a skeletal muscle. So let's say, I don't know, I'm doing Five Guys for breakfast, lunch, and dinner. So single burger for breakfast, double for lunch, triple for dinner, large fries, chocolate milkshake, and is that the place that mushes peanut butter cups into ice cream? I don't know, we'll say it does. And I'm doing that for small one for breakfast, medium for lunch, big one for dinner. So that's what I'm doing. So one day I'm walking around and all of a sudden I get really short of breath and I get left chest pain, left arm pain. Well, what's going on? Probably myocardial infarction, right? Probably a heart attack. So what's going on at a very basic level? Well, I've been doing garbage for breakfast, lunch, and dinner for however long. What have I done to my blood vessels? Well, I've damaged my blood vessels, including the ones that bring oxygen to the heart. And we'll talk about, I'm being very general with damage. We'll talk about that. But I've damaged the ones that are bringing oxygen to my heart, so my oxygen's not getting there. So what am I doing? What I'm doing is the Cori cycle over and over and over, because that muscle that just so happens to be my heart's not getting the oxygen it needs to make ATP to contract, relax, contract, relax. So I'm doing the Cori cycle over and over. So you rush me to the ER and you draw my blood, and lo and behold, I have a lot of lactate dehydrogenase in it. Years and years ago, that's what happened. The lactate dehydrogenase was used to say you're having a heart attack because I have the damage in my blood vessels. I have a cheeseburger stuck in my coronary arteries or whatever. I'm not getting oxygen to the heart. That's causing all the symptomatology, causing the myocardial infarction. And as a result, I'm doing the Cori cycle. I keep doing it, building up lactate dehydrogenase. That's how they knew what was going on. So that was done years ago. We have much more sensitive markers now, but I just wanted you to see the connection, see kind of the biochemistry rubber meeting the road in a sense. So that's, I guess, kind of the Cori cycle in action. Okay, so anyway, that's it for glycolysis. So this should be the end of your week one. You did the big picture, did glycolysis. And what I would do if I were you is I'd have my diagram that we did a few slides back. I'd have the full version of that. I did it in stages so you could see it better. If you want to separate it, separate it. The whole thing with the notes, they're by you for you. So if you want it all together, that works better studying, put it all together. You want to separate, multiple diagrams like I did, do that, totally up to you. So I would have that, and then I would have the Cori cycle with that also. When it was on paper, it was front and back of the page, or however you want to do it. And again, that's all you need to study for glycolysis, provided you've understood everything we've done. Always the caveat on that. So that's it for glycolysis. I'm going to have a bunch of questions for you. You'll go to those next. They're very representative, typical questions that you're going to see. Some of them are going to look a little repetitive on purpose because I want you to see the little variations. I'll probably, as time goes on, keep adding to those. I'll try to let you know when I do that. And then you'll go to your quiz from there. Then we'll move on to the Krebs cycle. Okay, see you in the next video.